Okay, next thing is derived data types. So what we already learned about data types, we provide them, are so-called the basic data types. That means the data types that correspond to language built-in data types. So it's MPI int for int, it's MPI integer for the Fortran version of the integer. We have MPI double as a C handle, MPI double precision as a Fortran handle, and so on. So, but now, as you probably as a programmer know, that data structures sometimes have to be more complex. Yeah? And sometimes you don't want to address just each one individually, yeah, but you want to have something that is more like a collective of something. Yeah? And MPI allows you to construct these descriptions of those data structures that you build as well. So again, a quick reminder, data types are again handle types. I also said this morning that you create a handle, you have to free a handle. If you didn't create the handle, you're not allowed to free the handle. So MPI int is a data type handle that is pre-created, that exists from the beginning. You do not free MPI int. You create your own data type handle. It's your responsibility or your code's responsibility to free those resources as well. Okay? So again, as a reminder, an MPI data type handle is just the instructions for the MPI library how to handle the data, either from taking it from your memory into the stream of either I/O or communication, or taking it from the stream into your memory again. Okay, the predefined basic types, they have a corresponding type in the language. And again, as a reminder, you have distinct types for C, C++, and Fortran. So it's MPI int for the C part, MPI integer for the Fortran part, but you can, in your communication, send from a C part of your application, because you can mix C and Fortran code in one application. You do that all the time, for example, if you link to a BLAS routine, because those BLAS libraries tend to be implemented in Fortran. Yeah, so, and if you have things like libraries that use MPI, but are also kind of like BLAS-like, they could be implemented in Fortran as well, and you call them from your C function or a C program anyway. Yeah, so there's some form of interoperability. So if you send an int, you can receive an MPI integer, as long as the code that's doing that, this is the C type, the C code is using MPI int, and the Fortran code is using MPI integer. So they describe a single data element, and we can construct or derive more complex data types, and we have an interface for that in MPI. So for example, if we have a matrix, yeah, this common example, it's also the example that we'll have in the exercise a bit, where we have rows and columns, we sometimes want to have the diagonal of a matrix, yeah, because that's the one of interest for sparse matrices, for example. Yeah, sometimes we have special data types for these special matrices, and we kind of want to construct those as well, and we want to make things transparent. Okay. Again, a reminder, there's the type signature and the type map. The type signature needs to match in our communication. So for here, we have like an int, and a double as the type signature. And as long as those match, in general, everything is good in our communication. The type map is something that is local to the process, because MPI is designed to be portable, even though like also portable across architectures, and even across architectures that are in the same MPI job. Yeah, at the moment, most of your HPC experience will be that you have some form of homogeneous cluster where you have where you have some or where all the nodes are basically have the same basic architectures. Like here, all of our nodes have Intel Sapphire Rapid processors. So even the ones on the GPU partition that have additional GPU cards in them, they still are Intel-based nodes. But for example, if in principle, again, the interface defines it that way, whether the implementation supports that, you would have to check. But for example, if you think, we have some test nodes with Grace hoppers. Grace hoppers are ARM, different architecture. Yeah, and if you would want to combine your application running on partly Intel and partly Grace hopper, so that is something where MPI, if the MPI library supports that, would kind of potentially have different type maps because the types have different sizes on those two architectures. So again, a long story short, the type map actually has the displacement from the start of the data type in it. And so here we have 0 because it's the first element. And then we have the second has a displacement of 4 because on this architecture, the MPI int is actually 4 byte, or the int is 4 bytes. So it tells you an MPI int will have a memory pattern of 4 bytes. And then the double here has the displacement of 8 because we have 2 ints. Potentially MPI should, or you need to take care that the addresses are correct. And we'll see that how we construct that. Sometimes MPI helps, sometimes MPI, you have to help MPI. But for example, if you do a struct of 1 int and 1 double, the second double will need 8-byte alignment usually. Yeah, and then this, if this entity doesn't have 8-byte alignment in the whole, you will have a gap in between. Or if it does have, then you'll have like this would be 0, this would be non-existent, and the double would still have displacement of 8. But there are ways to find out what the displacements are in your data structures and use that when you construct the derived types. Okay, again, data types are local objects. They just describe the local memory layout of your data structures. And we'll see how we can use that to our advantage, even though it's more or less of a toy example. Because in the exercises later on, we'll transpose a matrix in flight. So we'll read a column of a matrix and receive this, or like we send the column and receive it as a row. Or we send a row and receive it as a column. Both works. Okay, so yes, so then for if we talk about derived data types, we also now, especially if we now have gaps in them for alignment, yeah, with multiple elements, we usually have terms like a lower bound and an upper bound. The lower bound is the minimum displacement, and the upper bound is the maximum displacement plus a little bit of padding that is needed. Then with the upper bound and the lower bound, we can argue about something that's called the extent. And the extent is basically the upper bound minus the lower bound. That's the range that my data type spans. And that is also something that we need to keep in mind. If we have multiple counts of something, it always goes with the extent. So the next, so if I span, or if I send 2 elements of my derived data type, the second element, you only provide 1 start address. the address of the second element is right behind my extend. So that will be be important once we try to communicate multiple columns and so on. And then the size is actually empty. No, the size is the total amount of payload. Yeah, so it actually is, if it's the int and the character, the size on a normal machine like or a standard Intel machine that we have here in Aachen would be 9 bytes. 2 times 4 bytes for the integers and a single character, and that's it. So the size is just the payload. It doesn't account for any padding that's needed. Yeah, and those are 2 things that you need to remember how they're named. So we have a little example here. If we just have MPI int, the type map would be int 0 because the int starts at the first element. We have a lower bound of 0. We have an upper bound on 4 on an architecture where an int actually is 4 bytes. The extend actually is also 4 bytes. And the size is 4 bytes because we don't have any padding in there. So that's also something, all predefined basic data types have a lower bound of 0. That means the data is flush with the starting address. You can define derived data types in MPI that are not flush with the starting address. You do some manual massaging of the data type, and that's possible. And that makes it easy, especially for derived data types in file situations where you just provide a buffer, but you want this buffer to be written into a specific part of the file with an offset, and that offset is at the beginning of the file, and then that's how you can also manipulate the lower bound being non-zero. And then platform-specific alignment rules are taken into account, but sometimes you need to adjust the upper bound manually as well. So it usually does not align automatically on, if you, for example, have an integer buffer and you want to send every second element, right? What you want to do is your data type should have an int, a gap, an int, a gap. So, but the generation routines will cut off any gap at the end. So your data type will be like an int, a gap, and an int, and not an int, a gap, and an int, and a gap. And if you have more of those, then you will have int, gap, int, gap, int, which is not the pattern that's intended. And for those situations where you say, oh, I actually want that additional pattern that is not created by the compiler for me because it might be a valid pattern, there you need to modify the extend later on. Okay, so looking at a visual example here, so we have some form of pattern. We have like something like a double that has 8 bytes. We have a gap. We have an integer. We have a gap, and the same thing repeats. So our send type is supposed to be this with a gap at the end, yeah. And what we see is the send type actually puts this into some form of a data stream, yeah. Again, that's a logical view. It doesn't mean that the library actually packs things or repacks things. Potentially, hardware support will help you in there, or sometimes if you just send a large bit with little gaps in between, it's more efficient to actually transfer the whole thing because you have high bandwidth, and you don't want to chop that into small messages, and then you just transfer the gaps as well. So this is a logical view, and then the receive type will unpack this again, and it could be that here you don't have the gap. Yeah? because the receiver wants it this way. And this is how to understand the type signature matches, because we have a double and an int and a double and an int. But the sender defines how things are in the sender memory. The receiver defines how it is in the receiver memory. And we can send and receive those just as we used the normal basic data types. So now we dive into derived data types and how to construct them. And derived data types are named derived because you take a simpler data type and construct something more complex from it. And then you can take what you constructed as the basis for even more complex data types, and so on. So you basically derive a new data type that has a more complex memory pattern from a simpler one. Yeah, so you don't necessarily have to derive a new type all at once. Yeah. So as such, you have different creation routines that are a little bit simpler in their design, so it's easier to reason about them. Yeah, the most simple one is MPI type contiguous, and just has a count, an old type, and the new data type handle that is created from there. And as the name suggests, it says it is count elements of this type that are directly contiguous to each other. Please remember, it means that this type is contiguous here. It doesn't mean that this has to be a contiguous type itself. So if this has a gap at the end, so if the upper bound is basically, if the extent is larger than the size and you have an additional upper bound that that goes beyond the last element, you will have gaps in this, even though it's a contiguous type. It just means you take this data type and stick it right next to each other count times. Yeah. So, for example, as we'll see in the exercises, this is great if you want to send a row or an array in C or a column in Fortran, because Fortran is column major, C is row major in terms of memory layout. Yeah. Okay. And that's better. So if you can send if you think of a matrix, you want to send a row, okay, all of that is contiguous. But if you think of a matrix as one chunk of memory, a column now suddenly is not contiguous anymore, because a column has to skip the rest of the row until it comes to the next element in the column, and skip again, and so on. For Fortran, it's just transposed, right? So if you want to send a row, you have to skip the rest of the column, and so on. So how to define this is, again, you have a count, but now you also have a block length that tells you how many elements in one, let's say, column, or how many elements in this dimension do you want to be part of your data type. So for example, if you want to send 2 columns of a matrix at once, define that in one type, and not just have a single column type and then use that twice, then your block length can include 2 elements of this old type, and you can have a stride. And the stride is basically what you need to skip to get to the next element. Yeah, and it's from the beginning of the block length, not the actual gap. Yeah, it's like, what is the stride between the beginning of the blocks? Yeah, so stride in C would be the row length of, or the column length in Fortran, and in number of elements of that old type. Okay, so let's look at a visual example. We have 6 by 3 and matrix. Yeah, so thinking of this means this element is actually here in terms of my memory layout, right? So, so this is the first element. So this is displacement 0. I have a block length of 1 because I want to have one element in each of my things. I have a stride of 1, 2, 3, 4, 5, 6. And I have a count of 1, 2, 3. Yeah? So if I use this type, it is valid to use just a different starting address for this because the same things apply. I have 1, 2, 3, 4, 5, 6 as my stride. I have 1, 2, 3 count, yeah, and a block length of 1. Yeah, that's why I can reuse the same data type to transfer a different column. Maybe here, I don't know whether I bring this up in a separate example, but the extend is from here to here. That means if I use this vector with count 2, because I want to, for example, because I think I want to have this like a 2 column transfer, the extend is up here. So the next element, the next vector block or vector type block starts here and not there. Yeah, because it always goes by extend. Yeah, so that is something where we need to think about a little bit more complex structures on how to define those types if I want to reuse them. Okay, but I can have a block length of 2 and then send those 6 elements in one go. Still count 3, still count 6, stride 6, because 1, 2, 3, 4, 5, 6, but I have a block length of 2. Okay, so then, but now, so those are 2 vectors and they're very, very, all of these elements are very structured and very much the same. Yeah, I always have the same stride. And what if those individual blocks, yeah, if you think here, this is a block, this is a block, and this is a block. If I now think, what if those blocks are different for the things that I want to transfer? For example, I want to transfer the lower or the upper diagonal of a matrix in like a LU decomposition or whatever, right? And so now I still have a count. Now I have an array of block length because each block can have a different length. I have an array of displacements because each displacement can be different. From like each block could start at a different address or at a different element address. I still have a single count, so it can still just be all doubles or all ints or all my derived type, and I get a new handle out. Yeah? So, yeah, lower upper triangle, that's like a classic example that you can do, but of course, the idea here is how to map this concept to the data structure that actually fits your application, right? So this might not only be used for lower and upper triangles of your matrices, but any situation where you have different block lengths and different displacements. One thing with index that you need to keep in mind, because we're not talking about all the functions that are out there and so, in MPI, you sometimes will have to consult the manual for this. the standard itself, indexed has a displacement in terms of elements of old type. Sometimes, and especially with the displacement part, you have this displacement, like 1 has this, I'm going to the next extent, and there's another function called h-index, and that has a byte displacement. And that you can use to manipulate where the second count should start, and that it should actually start at the very top of your address again. But I think that's part of the bonus part of the exercises. So, but coming back to the normal indexed one, yeah, we would have an array of displacement. So, and here we see that our initial, we need to start. It's much easier for us as a developer to think of this still to be the matrix 0, 0, the start of the matrix. But I don't want I don't want to transfer this element. So that's why I need to, in the resulting element, I want to not transfer this element, and I want to manipulate the lower bound of my data type to make sure I skip a first row before I start sending this. So the array of displacements here is 5, yeah, 0, 1, 2, 3, 4, 5. Yeah, and then 10, 15, and 20. My block lengths are 1, 2, 3, 4, and I have 4 blocks in total. Yeah, and this how I would do this. I cannot use this for the upper triangle because the displacements are different. The block length would be opposite, so it would be like 4 first, then 3, then 2, then 1. Yeah, so in that situation, I would have to create a new type. We now jump directly. We skip a whole lot of other type creation functions. We skip directly to the most complex data type creation routine, which is MPI type create struct. Because a struct, with the struct, as if you think, I think a struct data type also is available in Fortran, at least the newer versions of Fortran. And in C, the data type of a struct is you can have arbitrary memory patterns in there. You can have an int, a double, a char mixed with another int and the pointer or something. So what you can do here is, again, you have a count. You again have different block lengths. You again have different displacements inside between the blocks. But now, not all of the types have to be the same, because in a struct, you can mix ints with doubles, with characters, and so on, right? And then you create a new data type. So now, here are the displacements, because you can have padding and things like that. The displacements are no longer element-based, because what is the element? What would be the element to skip? Because you have different types in there. Should you skip 4? Should you skip 3? Yeah, so that's why the displacements here are byte-based. Is that a question? Oh, okay. Yes, okay, so, and with that you can basically define full memory patterns in a sense. So you can also use this to have to define the lower or upper triangle in the matrix. It's just that you add one layer of complexity because it'll be all the same types. Yes, and that's why you have these more simple routines to help you and give you a simpler interface. Okay, so let's kind of look at this in a visual way again. We have type create struct, we have the count, the block length, the displacements, and then the types and the resulting data types. So displacement 0 here is where my data type starts. This is one block. That is the first block, so it's in block length 0. And this has a certain type. So that's in type 0. And then the second one says, okay, I start at displacement 1. I have a block length of 1 and the type of 1, and so on. And this is how basically those correspond to each other. And as we can see, at least from the width, yeah, that this one here on the third position is certainly different from the others. Yeah, but this could also be a long, and this could be a double, for example. Okay, so let's see how this might look in an example. We have in C a type def of a struct of my particle type. We have the mass of my particle, which is a float. We have a position relative to some form of a double inside my like a double value inside my three-dimensional continuous space, and I have to store some form of symbol to it. So the block length would be 1 float, 3 doubles, and a char, 1, 3, and 1. So this actually is also a dark bluish kind of thing, which correspond to this, and also to this, but it's not so easy to read. The contrast is not high enough there. So we have this blue is, and in C, you can basically use the built-in offset off to get the displacement, the byte displacement of this element of the struct from the start of the struct. And this is how you get the right displacements on your platform directly from the C compiler, and you can create this. And that's why it's also important that you basically compile your application on the target platform. But that also means that if you have these mixings of like ARM and Intel, this might actually be a completely different map here, type map here. And then the last one is an MPI float for the float, an MPI double for the double, and an MPI char for the character. And then you create this, and you call MPI type create struct, count 3, then the block length, the displacement, the types, and you get out a particle type. So with all derived data types, what you have to do before you actually use them in the communication, that's a little bit of what you need to remember, is that you so-called have to commit this type. So make it a little bit more known to the MPI that you actually want to use this in an actual communication, because these data type handles can have complex internal structures to describe the memory layout. And that description might be too complex to handle efficiently when you want to transfer something. Yeah, if you have linked lists and all sort of things, there might be nice if you want to later compose more things of this, but they might not be nice for handing this over to a DMA engine or something like that. So what commit will do, it'll make this data type ready that the communication engine of that MPI library can deal with this efficiently. You don't need to commit every type, only the ones that you want to use in a transfer or in file IO later on. So if you construct intermediate types, you only have to commit the last one that you actually going to use. But you will have to. And regardless of whether it is committed or not, you have to free the data type because you created this, so it's your responsibility to free this. Yeah, and basically, again, it's a handle. So every handle has a null type. If you freeze something, it'll be reset to MPI type null here, or MPI handle name null. Okay. So, so what we actually need to do here, because we want to send a single particle now, is we actually have to commit this, not just create the struct. The rest is basically the same. But now, what we need to, what we actually need to do is we have this awkward problem of the particle and the mass not actually being having a good alignment, and this is where you need to help MPI to do the right thing. So, in order to send multiple particles, you kind of need to make sure that you fix the data type, the extent for what is initially just the distance between the mass and the sim part. You have to use MPI type create resized, that you want to continue to start at 0, but now you want to have the true extent. You want to add yourself, you yourself want to add the correct padding to that type. Yeah, so that's where it's not exactly the compiler takes care of everything of the alignment. At the end, you sometimes have to help MPI to do the right thing. Because if you would have multiple particles, the compiler will take care that the correct padding between those elements is there, but you would have to you would have to make sure that the distance in the MPI type definition is there, and that's how you use it. The built-in size of the particle will tell you the padding at the end, and that is your new true extent, and you just say MPI type create resize, set the true extent, and then you can send multiple particles at once with this data type, no matter how complex this is inside. All right, so in summary, local handle on how to access memory of my process. Yeah, we can mix and match both sides of the communication as long as the type signature is the same. Yeah, but what also needs to hold in that definition is a single send matches a single receive. So I can't send a triplet in one send and receive that triplet by 3 single int receives or so. Yeah, it always has to be a single send matches a single receive. Upper and lower bounds can be manipulated to kind of fit the needs, like either add some padding at the beginning, add some padding at the end. Usually the padding in between is taken care of when you construct those things with the displacements that you have in the construction routines. So we need to commit before we use that in communication or I/O to kind of streamline and prepare the process to be used more efficiently in communication. Yeah, and because it's, yes, it is a kind of like an efficiency reason, it'll be an error of your in your application if you send using an uncommitted type. And because errors are fatal, your application will abort at that time. Okay, then again, data types, you have language-specific handles that you need to consider if you have mixed language applications, and that is basically all I wanted to say about MPI data types.